Now, we're going to end the year with velocity and acceleration. I think it's a very fitting way to end the year since we start the year talking about it. Suppose I define my position vector as x as a function of t in the I direction plus y as a function of t in the j direction. You know that velocity is a derivative of position. So velocity is a derivative of position. So we call this x prime in the I direction plus y prime in the j direction. You can also write this as x prime, y prime. So you can put it in the component notation. And acceleration is a derivative of velocity, or the second derivative of position. So we can write this as x double prime, y double prime. Now speed gets students on practically every AP test. Speed is the magnitude of the velocity vector. Remember, speed is what your speedometer says. It doesn't give you the direction. It doesn't have a direction vector on it. It doesn't tell you you're going southeast. It just tells you you're doing 65 in a 45. I know you wouldn't do that. All right. Now, suppose I have a position vector and I want to find all of the good things about it. The first thing you're going to do is find the derivative. So the velocity, and I'm going to label these. The velocity is r prime. So this is going to be cosine t over 2 in the I direction. And this is going to be minus sine in the j direction. So that's the velocity. The speed is the magnitude of the velocity. So this is the square root of cosine squared t over 2 plus minus sine t over 2 squared. Oh, well, that's simple. That whole thing's just 1. So the speed in this case is 1. The acceleration is the, I can call it the velocity, the derivative of the velocity, and I can call it the double derivative of position. Basically, I'm going to come back up here. So this is 1/2. Derivative of cosine is minus sine. Minus 1/2. It's cosine. It's the end of the year. All right. Now, let me show you something a little bit interesting. I'm going to factor this minus 1/2 out. What am I left with? I'm left with sine t over 2i plus cosine t over 2j. Now watch this. You're going to do this in physics. When you take physics, you're going to do periodic functions, and this is a trick you're going to need there. R is 2 sine t over 2 in the I direction plus 2 cos t over 2 in the j direction. So what if I multiply both of these by 2 and multiply the whole thing on the outside by 2? So I'm doing my algebra correctly here. So this is minus 1/4 2 sine t over 2i plus 2 cosine t over 2j. But what is this right here? This is just r. So this whole thing is minus 1/4 r of t. That's just kind of a cool thing. I like looking at these. Now, in physics, you were told the force is minus mg, and this is always going downward in the y direction, so that's why we have j. So when you're in a physics class and you're doing things, and you want to use calculus, you can do this conversion right here when you're doing projectiles. And acceleration is minus gj, where g is 9.8 meters per second squared, or 32.2 feet per second squared. Okay, so the acceleration is g. Let's look at this problem right here. If I have r of t is t squared minus 4i, plus tj, and I want the velocity and acceleration vectors at 2 points. Let's see if we can find them. The velocity is equal to r prime of t, which is 2ti plus j. So the velocity at 0 is just vertically plus j, and r prime of 2 is 4. All right, so if I come over here at t equals 0, all right, I see that the velocity is straight up. And if I come over to 2, I see the velocity is going over 4 and up 1. It's got that nice little slope there. Let me look at the acceleration. That's the second derivative. So this is 2. Oh, so the acceleration is always 2, no matter what. So at each point, the acceleration is pulling back to the right. Now, what do you do if we have to go backwards? An object starts from rest, all right, which means the velocity vector is 0, 0, 0. Okay. And the initial point is 1, 2, 0. It moves with an acceleration, which is j plus 2k. Now find the location. So we're going to look for position at t equals 2. So if I start with acceleration, the velocity is going to be the integral of this. So it's going to be the integral of dt in the j direction plus the integral of 2 dt in the k direction. So this is t plus a constant in the j direction plus 2t plus a constant in the k direction. Now there wasn't an I direction on here, and that is going to be a little bit tricky because you do have to add in the integral of 0 dt in the I direction. You remember that the integral of 0 is just a constant. And I will switch these back around in a minute. So I know the velocity at t equals 0 is 0, 0, 0. So the velocity at 0 is c3i plus, when I plug in 0 here, I've got c1j plus c2k. All right, but it started from rest, which tells me this term is 0, this term is 0, and this term is 0. That doesn't happen very often, but it does in this case. So the velocity vector is tj plus 2tk. Now I want to find the position. So the position, it's going to be the integral of velocity. So it's going to be the integral. Now you see I can't ignore this time of 0 dt in the I direction plus the integral of t dt in the j direction plus the integral of 2t dt in the k direction. So this is c1 in the I direction plus t squared over 2 plus c2 in the j direction plus 2t squared over 2, so it's just t squared plus c3 in the k direction. Now I know my initial point at is 1 in the I direction plus 2 in the j direction plus 3 in the k direction. And that tells me c1 is 1. Let's see, what is c2? At t equals 0, c2 is 2. And at t equals 0, c3 is 3. So I ran out of room here. I was afraid this was going to happen. So S of t is equal to I plus t squared over 2 plus 2j plus t squared plus 3k. Now, at t equals 2, what is S of 2? Well, it's I plus 4 divided by 2 is 2, plus 2 is 4j, plus, so this is 4 plus 3 is 7k.